Good morning student, myself Melissa, and in today's session we start our new method, that is conjugate beam method in slope and deflection unit. Okay, now before starting why we use this conjugate beam method, first we learn our Macaulay's method, but this Macaulay's method is tedious method and time consuming method. Then we use moment area method. Moment area method is useful for cantilever beam. Okay, but in analysis of simply supported beam this method is little bit tough, so that we use our third method, and that is conjugate beam method. Okay, first of all, define the conjugate beam theorems. Okay, we define conjugate beam because conjugate beam theorem is in two parts. First is slope and deflection. Okay, now what is conjugate beam? Conjugate beam is imaginary beam and length of this conjugate beam is same as actual beam. Okay, again I am repeating you, conjugate beam is our imaginary beam and length of this conjugate beam is same as actual beam. Now our beam is loaded with M upon EI diagram such that slope and deflection we find out here. When our beam is loaded with M upon EI diagram, then shear force and bending moment of conjugate beam is slope and deflection of actual beam. Got it? Shear force and bending moment of conjugate beam is slope and deflection of actual beam. Okay, here we assume the beam, then we apply load on beam and find out shear force and bending moment, and this shear force and bending moment is the slope and deflection of actual beam. Okay, now next, what is the difference between real beam and conjugate beam? Okay, now first difference that we discuss in definition, that is conjugate beam is imaginary beam and our real beam is our real beam, and that is used for construction element with stand load. That means real beam is our structural beam and it is used for construction with given load. This is the first difference between conjugate beam and our real beam. Second difference, conjugate beam is a imaginary beam and here we use this conjugate beam to find out slope and deflection of our given structural beam. And third point, shear force and bending moment of this conjugate beam is a slope and deflection of our real beam. Again, for one by one, real beam is our structural beam and it is withstand with our given loading and used for construction. Conjugate beam is our imaginary beam and it is used to find out slope and deflection. Then shear force and bending moment of conjugate beam is a slope and deflection of actual beam. This is the difference between real beam and conjugate beam. Now our next theory, support condition in conjugate beam. It is very important because in example we change the support condition. Okay, first of all here I mentioned the real beam support and after convert into the conjugate beam support. First, hinge support is real beam is as it is in conjugate beam. Hinge support is hinge support, there is no need to convert here. Then roller support is again in roller support conjugate beam, and in real beam fixed support is given and this fixed support is converted into free end. Okay, and this will be happen in cantilever beam. Okay, now in real beam our free end is converted into fixed end. Now internal support, that means here internal hinge is given. Okay, here look at this, this is our internal support is given and this internal support is converted into the internal hinge. This is all support condition of real beam will convert conjugate beam, and if internal hinge is given then this internal hinge is converted into internal support, and this internal support is nothing but that is our internal roller. Okay, this is the support condition of real beam and conjugate beam. Now properties of conjugate beam. Okay, here we discuss what is the properties of conjugate beam. The first property of conjugate beam, the length of conjugate beam is same as actual beam. This we already discussed in definition. Length of conjugate beam is same as our actual beam. Now second property is the load on conjugate beam is M upon EI diagram, that is load of actual beam. Okay, now when we load the given beam with M upon EI diagram, this beam is conjugate beam and this load is applied on actual beam. Okay, first imaginary beam, our conjugate beam is imaginary beam, length of this conjugate beam is same as our actual beam, and our given beam, that means conjugate beam, is loaded with M upon EI diagram, and this is the load on actual beam because it is actually a imaging beam. Now simple support of real beam is as it is in our conjugate beam, there is no change in simple support. Then fixed end of real beam is converted into the free end, and important thing, point of zero shear for conjugate beam corresponding to point of zero slope in real beam. Okay, if we find a point of zero shear in conjugate beam, in actual beam at that point slope is zero. Again repeat, in our conjugate beam if we find out point of zero shear, that means at that point slope is zero in our actual beam. Okay, same with moment, point of maximum moment in conjugate beam, that means point of maximum deflection in real beam. The point where we find out maximum bending moment in conjugate beam, at that point we find out deflection at maximum at that point. Okay, this is some properties of conjugate beam, and next we solve our first example of conjugate beam. Okay, our theory portion is complete here. In theory portion we learn definition, second we learn the support condition and properties of our conjugate beam method, and the remaining thing I will explain you at time of example. Okay, next we solve our first example of conjugate beam. Okay, now we solve our first example of conjugate beam method. Before starting this example, we read the given data properly. Okay, calculate, that is phi b and yb. Phi b means our slope and yb means deflection for cantilever beam loaded as shown in figure, where E is given 200 gigapascal and I is given 5 into 10 raised to 8 mm raised to 4, and find out conjugate beam method. Okay, deflection and slope we find out at B point. First of all, Young's modulus E is given 200 gigapascal. So we convert this gigapascal into Newton per mm square. So 200 10 raised to 3 Newton per mm square. Okay, and moment of inertia I is equal to 5 into 10 raised to 8 mm raised to 4. Now here two loading is given. First load is our UDL and second load is our point load. Okay, this A, C and here is our B point, and this point we find out slope and deflection. Here we find out moment of two load are different because BM diagram of point load is inclined, so we take area 1/2, and BM diagram of this UDL is inward parabola and we take area from 1/3. Okay, so we find out separate bending moment for point load and for UDL. First of all, mention here bending moment due to UDL. Okay, bending moment due to UDL. Okay, and this we find out from right to left. Again, our first point is MB point, second point is our MC point, and third point is our MA. Now at B point UDL is start, so moment of MB is equal to 0. And at C point UDL is given and moment of this UDL is equal to 20 into 2 and 2 by 2 minus 20 and distance 2 meter and 2 by 2. Okay, and my moment 2 cancel and answer is equal to 40 kilonewton into meter. Now moment at A, that means A point, 20 into 2. Okay, what is the moment at A point due to this UDL? 20 into 2, and A point, our CG, is equal to 2 plus 2 by 2. Okay, right here 2 plus 2 by 2, and my answer is equal to minus 120 kilonewton into meter. Second we find out, right here, second we find out bending moment due to point load. Okay, our second load is equal to point load. Now first point is again MB, second point is MC, and third point is MA. At B point, point load is given, so moment is equal to 0. C point, 40 into 2, right here, minus 40 into 2 is equal to minus 80 kilonewton into meter. At A point, this 40 into distance given 4 meter, so right here minus 40 into 4 is equal to minus 160 kilonewton. Now one by one we draw the BM diagram for particular loading. First of all, mark the point A point, C point, and here is the B point. Here I draw M upon EI diagram. Right here, this is our M upon EI diagram for UDL load. Okay, and in below M upon EI diagram for point load. Okay, now at B point moment is 0, at C point we get moment 40, and B to C UDL is given, so our diagram is inward parabola. Okay, like this way. Complete this diagram, and here at this point we get 40 by EI, and here I get value 120 by EI. Now we solve this example with conjugate beam method. So first of all, we make this free and as fixed. This is our B point. Okay, and minus diagram, given number of forces are indicate in upward direction. Remember that if our diagram is negative, forces are in upward direction. Distance is given 2 meter, this distance is given 2 meter. Okay, and here is our first area because here is inward parabola, and complete this, make this extension here. Okay, this value of this rectangle is equal to 40 by EI. So below one is equal to 120 minus 40 is equal to 80 by EI, and overall diagram is minus. Now this is the point load. Again A, here C point, and make this free and fix, and fix and free. Okay, distance is equal to 2 meter, and this distance is equal to 2 meter. Okay, first we find out this point is equal to 80 by EI, and at second point we find out 160 by EI, and diagram is minus, so forces are act in up direction like this way. Now this point is our B point. Here I consider one area because point load is given 1, and we find out slope and deflection at B point. If 2 point load is given, then I separate this diagram, and if in data ask find out theta C and del C, then we again separate this diagram. But in example, find out slope and deflection at B point only. That means here we cover whole area, and if we divide part, this triangle, this rectangle, and this triangle, ultimate summation of this total area 1 to 3 is equal to total area of this triangle. Okay, so here I take one area. Now next we find out one by one our slope and deflection, because here we use moment area method, conjugate beam method. So first again complete this A point, C point, and make this free to fix, and given point is our B point, inward parabola. Okay, this point is given 40 by EI. Simply I take values because figure I explain you. Okay, this one is 40 by EI, and 80 by EI minus, and forces are in up direction. Same here, make this phi, and total height is given 160 by EI and forces are in upward direction. Total distance A, this point is C and this point is B. Okay, distance is given 2 meter and 2 meter. Same here, distance is given 2 meter and 2 meter. Now first of all we find out theta B. So right here, theta B is equal to slope at B in conjugate beam, slope at B in conjugate beam is equal to SF at B dash in actual beam. Slope at B in, sorry, here we write down, make correction because actual beam is subjected to, here we write in this portion actual beam is subjected to, okay, change the condition because slope we find out in our actual beam. So right here, slope in B, slope at B in actual beam, because in definition we already learned, and SF at B dash in our conjugate beam. Okay, conjugate beam. Now make here we change the sign, A dash, C dash, B dash, A dash, C dash, because these are our conjugate beam, or we can say that this is our M upon EI diagram. Right here, this is our M upon EI diagram, or we can say this is our conjugate beam. Okay, conjugate beam. Now one by one for theta B. First area is here 1/3 right here. Okay, and here according to our sign convention, upward, upward, downward, downward, plus, minus, minus, plus. Here we follow the forces. If we stand at B point, given number of beam is on left hand side, and at left side forces are in upward direction, and this up direction forces at left hand side is positive, so we take this diagram directly positive. Okay, now first area is this inward parabola 1/3 right here, 1/3 into distance 2 meter, and height is given 40 by EI. Second area is our rectangle right here, plus 2 into height is given 40 by EI. Then again this triangle 1/2 into 2 into height is given 80 by EI, and our last area of this triangle due to point load 1/2 into distance 4 divide by 160 by EI, and my theta B is equal to 506.67 divided by EI, and numerator is in kilonewton into meter square. Now in example, value of phi and I is given Newton mm, so we convert here. Theta B is equal to 506.67. Kilonewton is equal to 10⁻³ Newton, and meter square is equal to 10⁶ meter square. Value of E is equal to 200 into 10⁻³, and I is equal to 5 into 10⁸, and my answer is equal to 0.005067 radian in clockwise direction. Okay, next we find our del B. Again here find it, del B, write down. First of all, del B is equal to deflection in actual beam is equal to bending moment in conjugate beam. Okay, conjugate beam at B dash. Again we complete this A point, C point, and this is our B point. Inward parabola minus, okay, 40 by EI. Again this convert, okay, 80 by EI, 40 by EI, and this diagram 160 by EI. Fix this here also, fix this 2 meter, then 2 meter, okay, A point, this one is C point, this one is B point, okay, B. Now one by one we take area into CG. So right here, okay, and given number of forces are upward, and these upward forces rotate in clockwise direction, left hand side clockwise positive, so here we take positive. Okay, now first area into CG, first 1/2 into 2 into 40 by EI, and CG from this point is equal to 3/4 of 2, okay, because inward parabola. Again I am repeating you, this is inward parabola, so 1/3 into 2 into 40 by EI, and CG from this point 3/4 into 2. Now second is our rectangle section, 2 into 40 by EI, and take CG from this B point. First add extra distance 2 and 2 by 2, okay. Then again our triangle section, 1/2 into 2, and height is given 80 by EI CG. First add this extra distance 2 meter, and 2 plus from apex CG is 2/3 into 2. Next our last is this moment diagram with the point load, 1/2 into 4, and height is given 160 by EI, 160 by EI, and CG from this B point is equal to 2/3 into 4. Now my del B is equal to 1400 divided by EI, and unit of this numerator is kilonewton into meter cube. Now convert 1400, 1 kilonewton, Newton 10 raised to 3, meter cube mm cube 10 raised to 9, divide by EI 200 into 10 raised to 3, 5 into 10 raised to 8. Now del B is equal to 14 mm, okay, and value is positive, so it indicate in downward direction. Okay, here we solve the example of this cantilever beam with conjugate beam method. Okay, now in next session we solve another example. Okay, just now we stop here.